numbers and the way they accumulate over multiple time steps. Then the final slide is just the list of references. So if anybody wants to learn more about any of these topics. Thank you.
Thank you. And we have also one question only.
Yep.
If we can take 1 minute, maybe it's a bit too long. Actually, we are short in time. But maybe
okay,
Mike,
sorry,
can you answer in the chat?
Yes.
During the next talk. Yes,
yeah.
yes, because we have to move on to the next talk. So maybe Habib can join us now for the next talk. So thank you so much, Habib. So uncertainty quantification in large-scale computational models, very clearly fitting today's topic. Please go ahead.
Can you see my screen?
We could see your screen, but now it's becoming, it became black. I don't know if it's the same for everybody.
How about now?
No. We could see your screen just earlier, before it became black.
Yeah, I went to full screen. Let me try now again.
Yeah, we can see it.
Is that big enough?
Yes. Yeah, this is better. Yes.
Okay. Okay, I'll go ahead and start. Thank you for having me. I wanted to talk about UQ in large-scale computational models. This talk will essentially describe our experiences in applying UQ in large-scale problems and what we feel are best practices in that context. This work is a result of a number of projects funded by agencies of the US government, as well as a result of collaborations with a large number of people shown here. So I want to start by saying that basically, if we talk about forward UQ, propagation of uncertainty from inputs to outputs of a computational model, and we consider specifically methods based in probability theory. Essentially, what we're talking is about a PDF on the input, and we want somehow to propagate this to the output of the model. So the simplest construction we can think of is a random sampling of the PDF with Monte Carlo. And you generate samples of X from its PDF. You compute all the samples of Y, and you bin them to construct the density on Y. And there are many ways that you can do this. In general, however, this is not a feasible strategy for large, expensive models because of the slow convergence. Of course, the convergence rate of Monte Carlo is insensitive to dimensionality. That will come back and be an important piece of the answer. But still, in general, it can be an expensive thing to get good estimates of quantities of interest. So invariably, if you look at the UQ developments over the past 20 years, the focus has been some way of achieving a good surrogate for f of x. That's essentially what the forward UQ field has been about. You can use interpolants, you can use regression, you can use Galerkin methods, which have been used a lot with polynomial chaos methods. But essentially, all of that is about proposing a simple function, quite often composed of orthogonal polynomials, and fitting it two samples of your true function, and then using that surrogate now with Monte Carlo or otherwise to compute quantities of interest instead of using the true function. Of course, the devil is in the detail and specifically in dimensionality. All of these methods that have to build a surrogate have to deal with the fact that in high dimensional systems, this becomes a worse nightmare than the challenges with Monte Carlo for good quality estimates. I would say, while I'm talking here about forward UQ, surrogates are necessary for inverse problems, of course, in Bayesian inference or otherwise, as well as for optimization. So the building of a surrogate is really quite fundamental to a lot of things we do in UQ. And high dimensionality is a key challenge. And so let me focus on high dimensionality specifically. High dimensionality is a result of large number of uncertain inputs. If you have random fields, it might be the high level of resolution of the random field. But generally, you are in a context where you have a high dimensional input space. And while we would like to use sparse quadrature to get accurate estimates of these surrogates, doing sparse quadrature in high dimensions does not provide a viable answer. Ultimately, Monte Carlo is better in very high dimensional systems. And a key point about Monte Carlo is really important to remember. And this is why it is very useful in practice, is while the dimensionality of the surrogate goes up with the input dimensionality, and the associated difficulty of building a surrogate is requiring a large number of quadrature points goes up equivalently. With Monte Carlo, it's different. Actually, the quality of the estimate you get from Monte Carlo depends not on the raw dimensionality that you proposed, but actually on the number of important dimensions. And that is without knowing which dimensions are important. That's really the true magic of Monte Carlo. And I think we can fairly say that in physical systems, and specifically if we're talking about normal operation, we're not talking about failure modes. Failure modes are just a nightmare to deal with. But in normal operation, a physical system is generally controlled by a small number of inputs. And in other words, a small number of inputs are truly important, even though you may have a very high dimensional input space in your model. And so that's the saving grace of Monte Carlo, that it's true that you may have a high dimensional model, but there could be a handful of parameters that are actually important. And Monte Carlo doesn't care to know which ones they are. You will get good estimates if the input space is truly low dimensional in this way. However, while it's better than the alternatives, it's still expensive to take a lot of Monte Carlo samples when the model is expensive. So we're going to get into that. But in any case, my proposition is that the way out for large-scale models is that we use a global sensitivity analysis with Monte Carlo to identify important parameters. And then we go with your method of choice. For us, it's polynomial case expansions with sparse quadrature on the reduced dimensional space for more accurate computation of surrogates and therefore forward UQ. You can do sensitivity analysis in many ways. One of the most common ways in probabilistic context is estimation of fractional variances. And these are the well-known Sobol indices, which is a method that requires you to compute conditional estimates of these moments, variances and expectations. This is actually still expensive if used directly, on a large-scale model. So we still need to deal with the cost if we have a large-scale model. In other words, it still takes a large number of samples. And so when we couple high dimensionality and high cost of the forward model, our overall strategy is the following. We want to use global sensitivity analysis, but we want to introduce regularization through introduction of some type of smoothing, some type of information that the analyst proposes on the smoothness of the quantity of interest. And so presuming smoothness, what is quite effective is to use the Monte Carlo samples rather than directly compute sensitivity analysis from them, to use them to fit a function by regression, and we fit a PCE, which is then subsequently used to estimate sensitivity indices directly. And that estimation is quick. Now, this gives you a certain advantage, right? Because you're bringing in information in the sense of smoothness. It may give you bias, so you have to be careful. But in systems where you know you have a certain smoothness, you can take advantage of that. And I'll show you an example of that. But you also have to bring in sparsity, because to fit a PCE in, say, 1,000-dimensional space, where your parameter space can be, in fact, 1,000-dimensional, is quite a difficult proposition. You may not have enough data points from Monte Carlo to do that fitting. So you need to bring in constraints, and specifically compressive sensing constraints, to discover a sparse PCE. And so that's the important second piece of the puzzle, that this regression with the Monte Carlo samples has to be done using some constraint on sparsity. Otherwise, in the original native high-dimensional space, you have a problem. And finally, to deal with computational cost, we also use multilevel Monte Carlo methods as well as multilevel multifidelity methods to bring in information from models at different fidelity, at different mesh resolutions, and bring all of that into the fitting of this sparse PCE before we compute sensitivity indices. So this is generally the pieces that we bring together for large models in terms of a first stage of estimating a reduced dimensional space. We fit a PCE to the samples. We use L1 known constraints to regularize that fitting and get a sparse PCE. And the data we use will comprise of computations at different levels of fidelity or resolution. Once you've done that, you have a lower dimensional space, and we move forward with sparse quadrature or anything else you like to use. So I'm going to go a little bit faster now. So we want to estimate the Sobol indices with PC regression, and I want to just show some slides outlining the math very quickly in this area. So we have a PC expansion, a polynomial calculus expansion, as shown here. And we want to use the regression with random samples from Monte Carlo to fit that expansion. In other words, we're simply solving this fitting problem here. We're trying to estimate these coefficients of this polynomial expansion to fit a model to this representation. So that's easy enough to see. And then we use the expansion directly to estimate all of the Sobol indices. So you don't even need Monte Carlo from that point. And you can see the utility of this strategy here very quickly. This is a simple test problem, initially in 1 dimensions. And we're comparing error in sensitivity estimates from a different number of points for fitting this function. And on the left is Monte Carlo. And these points here show the increase in the surrogate order, the PC surrogate order that's fitted to that data, and then used to compute the sensitivity indices. So in 1D, the problem is really quite clear. You get a significant advantage from the PC smoothing in terms of an order of magnitude improvement in the error, and for a different number of points. As you go to higher dimensions, you can find a difference between the performance in order, but in general, you get this 1 to 2 orders of magnitude improvement in the error. And this is with no cost to you. You have done the same number of Monte Carlo samples. You have run the risk of introducing some bias, so you have to know what you're doing with the presumed model. But fitting a model first and then computing sensitivity indices is a significant gain. The sparse regression to fit the model can be done in a number of ways. I have listed some of them here. These are all standard in the literature. In general, you want to solve some optimization problem to minimize the L1 norm in some form or other. It can be imposed as a constraint, as in LASSO, or an unconstrained LASSO as part of the regularization of the objective function, or you have basis pursuit denoising. So there's a lot of ways that you can introduce sparsity using L1 norms whenever you have this situation that the number of parameters in the model is so large because of the high dimensionality that you don't have enough points to really provide good fitting. Okay, so that's quickly on sparsity. And one important point, with the unconstrained, illustrated here with unconstrained LASSO, but in general, it's an important point for all of these methods where you have a regularization parameter as this lambda here in applying the L1 constraint. You also need to figure out what's a good choice of lambda. And this you can do with cross-validation strategies. And we have done some work in doing k-fold cross-validation to estimate an optimal lambda for the fitting that you're trying to do with these samples. So this can be done. It's part of the work required to do this type of regularization. And you can do the regression with regularization, in other words, with sparsity constraints in a Bayesian setting. And I won't go into detail. This is just quickly covering Bayesian regression in applying priors that are essentially Laplace priors that enforce sparsity in a similar way as L1 constraints. And Bayesian compressive sensing is a method that's been in the literature for a while that I won't go into any detail. So I want to show some demonstrations. This is an example in Computations that we've worked with people at Oak Ridge National Lab, Brian Worth and Sophie Blondel, as well as others that contributed to this project. This is work on analysis of material damage for the ITER fusion reactor. And in this context, we're using a cluster dynamics code to model the damage processes associated with energetic nuclei hitting the wall and causing damage to the wall through various processes of introducing interstitial helium in the wall material, as well as voids and the movement of these voids. And so it's a large code that models the damage processes at the wall. And I'm not going to talk about any of the physics, but I want to talk about the UQ results. So here's a global sensitivity analysis in this code. And the plot on the left shows the first order Sobol indices for this 8-parameter system with 400 samples, which is what we could afford. And what you're seeing is that with 400 samples, if you don't do anything, this is direct computation from the Monte Carlo samples, you have this, of course, unphysical result that you're getting negative estimates of these conditional variances. That's just noise in the results because of poor convergence. And if you go to first least squares fitting with a PCE, you can see that you first get rid of the negatives, you reduce the noise in this region. And if you introduce sparsity on top of that, you can see that the system is much less noisy, and in these higher energy, higher parameters, or parameters with lower uncertainty, sorry, with lower sensitivity, and that is the result of sparsification. This degree of noise is due to overfitting, which the compressive sensing is avoiding for you. And I mentioned that this is done with 200 samples versus 400 samples at this point. So that's the kind of advantage we're looking for. And then I will say only this slide about multilevel multifidelity methods. I think if you think of multilevel Monte Carlo or multifidelity methods in general, I feel that these are crucial strategies for any UQ in large-scale modeling. There's simply no way around it. When the model is expensive, you need to take advantage of information from lower quality computations that you can do. And I won't talk more about this. Mike has already talked about this and explained these methods. So I feel that this is a crucial piece when we get to really large models. And I want to basically say that this is, in general, the framework as we see it, that you start off with a high dimensional model that's quite expensive. You have a number of resolutions, I call them levels here, level 1 to level M, that are options for you. You have a number of fidelities. Ultimately, you can have a 1D model, 2D model, a model with different kind of subgrid modeling. And so broadly, you have some multi-level multifidelity strategy to use these models to provide estimates. And these estimates go into your global sensitivity engine, which relies on polynomial smoothing as well as sparsity to get you clean results. And this ultimately, coupled together, this is a bidirectional arrow because the multilevel multifidelity machinery has to detect what the samples are doing, how much do you have correlation between low and high fidelity models in order to generate samples in an optimal way. And that provides you ultimately the low dimensional model that you want. And in the last few minutes, I want to go over a really difficult application that we worked with, bringing all of this machinery together. This is a simulation of a scramjet. A scramjet is a combustion engine that has no moving parts. You can see this picture here, schematic of a scramjet under a jet plane. It's simply an open channel in which air comes in the front, fuel is injected inside the body, and then mixing and combustion happen simultaneously, and then you have the high temperature gases going out the back. It's a supersonic system, and the ram part is about the ramming of the air. It's a ramjet effect in compressible flow. So these are designs for high Mach number flight. And we worked on a project where we're computing a lab version of this. The lab design is something like it's shown below in these schematics. I hope you can see this is an engineering drawing of a system with an incoming channel that opens up into a chamber where the combustion happens. Then you have the exit nozzle, and this is a overview cut that shows the transversal direction. This is an example of the type of computations that we run. We have the inflow, you have combustion in this system, and outflow model here. These are, as you can imagine, very expensive computations. You have turbulence, you have flow physics, you have chemistry, and you have spray because you're introducing liquid spray. The code is by Joe Offerline, who is now at Georgia Tech. I won't say anything about this. There's a lot of work that has gone into this over decades. It's highly scalable on large computers. It can do 3D reacting flows under conditions that are relevant in these systems. So I will let that be. Here's some example computations in 3D, just to give you a picture of the flow. We have temperature here, where the flow comes in. You have the reaction starts in this region and moves downstream. But let's get to the UQ bits. we used both multi-level and multifidelity here. So we have model A to model Z in general, where we're increasing model fidelity. And we have grid 1 to grid G, where we're increasing grid resolution. And generally, as Mike indicated, you rely on these telescopic sums to provide you the ultimate answer. I won't go into any of the details. Multi-level multifidelity methods involve a lot of diagnostics of the samples to do optimal sampling, and there's a lot of literature on that. And we used these types of measures of correlation between low fidelity, high fidelity samples to design what number of samples we run at low and high fidelity. So the specific realization of this for us here is that we have fidelity in terms of going from 2-dimensional large eddy simulation to 3-dimensional, and then we have fine grid to coarse grid. Okay, so that's basically our picture. And you know, we have a 24-dimensional system. We can only afford to take a very small number of the high fidelity runs. We, in general, have this type of cost pattern. So if the 2D D/8, which is coarse resolution, has a cost of 1, then the 3D high resolution is about 2,000 times more expensive. Okay, and we're interested in computing all of these expectations for physical quantities in the flow in terms of quantities of interest you need. These are the parameters. As I said, we use all this number of runs, ultimately doing 11 on the fine grid 3D runs. Here's the sampling of the results. So this is a way of illustrating the sensitivity analysis results with either multi-level or multi-fidelity, and we're showing the two separately. But of course, we bring the two together also. And on the plots, you see on the vertical axis are the various quantities of interest that you're looking for. And on the x-axis are all the parameters in the model, right? So the color map indicates what's important. So here, the two parameters, Li and Mi, whatever they are, I'm not going to get into that, are important here and need to be known. And similarly, the multi-fidelity perspective also provides that. And so you bring all of that together to get the reduction you're interested in. And I will just show some pretty pictures of the mean flow quantities computed from these samples in the 3D flow. You can imagine that there's a lot of interesting questions you can ask about, for example, some regions where the mean quantities are particularly high, as well as you can look at the variances. This is sorry, the standard deviation and the mean of the pressure, standard deviation and the mean of the temperature, etc. So I believe I'm out of time. This is more pictures of different quantities in the flow. I will simply close with this slide. I think from my perspective, a necessary workflow for UQ and large-scale models is you need to rely first on Monte Carlo for global sensitivity analysis to cut dimensionality. And for our purposes, we rely on polynomial chaos regression with L1 norm constraints for sparsification, and we bring in multi-level multifidelity methods for the sampling. And then we move on to adaptive sparse quadrature methods, and then these surrogates can be used in forward or inverse UQ methods. Okay, there are many other avenues to find low dimensionality, low dimensional importance spaces. You can use these Monte Carlo samples to do basis adaptation, active subspace methods, manifold discovery, etc. There are different ways of doing this, but in general, it pays to use the samples to find a lower dimensional space and then do what you want with the lower dimensional space. And the final caution that in high dimension, in large computational models, which are expensive to run, where you can only afford to take so much time of averaging to get statistics from any one sample. These flows are dynamical flows. The results, the QIs are noisy, even though in principle there's no noise in the system, but this is the sampling noise of averaging over finite time windows in the dynamical context. And so quite often this is an issue, and this is an issue we have to deal with the multifidelity perspective because these are noisy functions effectively. So with that, I will finish and thank you for your attention.
Thank you so much. So there's no question yet in the Q&A, but I invite attendees to ask questions, and maybe Habib will answer them in the break, or maybe Habib deserves a break after a nice talk where we navigated across low dimension, multifidelity, multi-level. It was very, very helpful. And I'm sure there is a lot to discuss under the hood. It seems to work very well, but it's complex to implement and orchestrate, let's say. So now we have a break.